Welcome everybody once again. So we have completed our 4 modules and today we are going to start our 5th module. So our 5th module is about beams curved in plan. So you already know the beams not curved, that is straight beams, right? You have seen the beams either with fixed support or hinged support or simple supports, and they are not curved in plane. So you may see some beams that will be curved in plane. Examples are arches. Okay, so if you imagine arch, so arches are actually the beams and they have some initial curvature, and this curvature will be visible only in the elevation, not in the plan. But there are some beams which will be curved in plan also. We are going to analyze such beams. Okay, so our 5th module is about beams curved in plan. In plan also the beams will be curved. So for such beams, see, you already know how will you do the analysis of a structural element is. We will be finding the shear forces, bending moment, deflection. So these are the 3 important factors which you will analyze while analyzing any structural elements: shear forces, bending moments and deflections. So here in curved beams we have shear forces, bending moments. So moments, in addition to bending moments, you have torsional moments also, twisting moments also. Okay, so if you have a curved beam like this, see, when you have a straight beam, when there is a load acting on any part in the beam, the moment, bending moment will be equal to the load multiplied by the distance, multiplied by the perpendicular distance. Okay, so since it is a curved beam, when there is a load W acting at some point, when you are taking a section X, your bending moment will be equal to this load multiplied by the perpendicular distance. So you can draw the perpendicular distance, you can draw a perpendicular line from the point of application of the load W. So moment will be equal to W into perpendicular distance. We are taking this as A, this as B, C. So perpendicular distance is AC. So bending moment will be equal to load into perpendicular distance, and your torsional moment will be equal to the load multiplied by, see, this distance. This is one perpendicular line, this is another perpendicular line. So this AB multiplied by AB will be your torsional moment. So when a beam is curved in plan, you will have shear forces, you will have bending moments, you will have moments, you will have bending moments and twisting moments or torsional moments. Then when there is some loads, you can find the deflections also. There will be deflection at various points of the beams. So you have only few examples. Okay, so first example is a curved beam is in the form of a quadrant of a circle of radius r and having a uniform cross section in a horizontal plane. It is fixed at A and free at B as shown in the figure. So your given beam, your given curved beam, your beam is like this. So this forms a quarter circle, okay, hinged at one end. So your given beam is A, B. So if you extend this A and B, and you can take this point as O will be the center, and you can form a circle with center O and radius equal to OB or OA. So OA is equal to the radius R, OB equal to the radius R. So this is your beam. AB is your curved beam, and this AB forms a quadrant of a circle. Now, so it is fixed at A and free at B. Okay, fixed at A and this end is free end. It is not hinged, it is free end. Okay, B is free end. It carries a vertical concentrated load of W at the free end. So at B, you have a vertical concentrated load of W. Compute the shear force, bending moment and twisting moment values and sketch the variations of the above quantities. You have to draw the shear force diagram, bending moment diagram and twisting moment diagram also. Also, determine the vertical deflection of the free end B. You have to find the vertical deflection at the free end B. So, how can you analyze this curved beam? Okay. So, now see this is similar to cantilever, right? End A is fixed and B is free. That means it is a cantilever. We know cantilever beam is statically determinate. So that means your curved cantilever beam is also statically determinate. So our first conclusion is the given cantilever is statically determinate. So indeterminacy is equal to 0. It is a statically determinate. Now we will consider any point X on the beam at an angle theta from OB. See, our first aim is, first of all, we will try to analyze for the shear forces. Okay. So case step 1 we will do. We will write step 1. We will try to find the shear forces. We are going to analyze shear force. So for analyzing the shear force, we will draw the curved beam. Okay. So this is A, it is B here, and we have the point O. Now, consider any point X. So consider any point X on the beam. So we know beam is AB on the curved beam at an angle theta from OB. So from OB, you take a section X. So we can take the section X. Let us take section X, and this X is making an angle of theta from OB. So this angle is theta. Now we are going to find shear force at this section X. So for that, we know what is shear force. Shear force is the summation of all the forces, right? Summation of all the forces either to the right of the section or to the left of the section. So here you have a load, concentrated load W at B. So shear force is nothing but summation of all the forces either to the right of X or to the left of X. That is all the forces in this portion AX or summation of all the forces in the portion XB. See, we know when there is a cantilever and when you take, for a cantilever always we will take the shear forces from the free end. We will analyze it from the free end in order to make our analysis simple. So, when there is a load, when there is a downward load W, see, we know shear force, the left upwards and right downwards is positive, right? So here also we have downward force from the section. If you are considering the right of the section, free end of the section, there is a downward force. So that will be positive force. Okay. So, and see, shear force is independent of theta. Shear force is independent of distance. So it is independent of theta. So we will take the shear force as F theta. So F theta is independent of theta. It do not depend on theta. That is all. It do not depend on theta because it is summation of all the forces. So what we get is at B, the shear force F theta F theta will be equal to W because positive, right? And up to X, at X, you take at X, shear force, the summation of all the forces to the right of X. We get F theta is equal to W. You can take at A, shear force is equal to summation of all the forces to the right of A. We have only W, so W. So at B, your shear force is W. At X, shear force is W. At A, shear force is W. So everywhere the shear force is W. Okay? Everywhere the shear force is W. So how will you draw the shear force diagram? So we will draw the corresponding shear force diagram here. So our beam is like this. Our curved beam is like this, right? This is A, this is B. This is the center O, center of the circle O. So it is positive everywhere. It is positive everywhere. So from B, at B, W, it's positive W, right? Okay. Okay. At B, it is W. At X, it is W. At A also, it is W. So everywhere it is constant. So positive, right? So everywhere it is positive and the magnitude of the shear force is W everywhere. So here also it is W. This magnitude is W. So this is called your shear force diagram. Shear force diagram for your given curved beam, right? So this is a cantilever curved beam forming a quadrant of a circle. So first part of your analysis is over. So the second part is the determination of bending moment, right? So first part of the analysis is over. Second part is the determination of bending moment. You will take the same diagram. So step 2, bending moment. So for bending moment, you are considering the same section X. Okay? Consider the section X. Now, for finding the bending moment, we know bending moment is equal to the load into perpendicular distance. So, for finding the perpendicular distance, so your load is acting at B. So, from B, you draw a perpendicular line. From B, you draw a perpendicular line meeting OX. At some point, we will take this point as C. Okay? In order to find the perpendicular distance, You are drawing a perpendicular line from the point of application of load towards the section X. So, this point is taken as C. That means your bending moment at this section will be equal to this load into perpendicular distance, W into BC. Now, how will you consider this sign? So, bending moment at X. Okay, that is bending moment at section X is M. We will take M as bending moment. So, M theta, because this section X is making an angle of theta with the horizontal. With respect to this point B. So, M theta is equal to, how will we take the section? See, we know for the bending moment, when we are considering the section, the load is acting downwards, right? W is acting downwards. So, left clockwise is negative. Similarly, right clockwise is negative. Similarly, left anti-clockwise is negative, because when you are considering a section, so your hogging moment, you will have hogging moment at the supports, right? If it is A and B, if you have hogging moments, see, this is clockwise moment, right? So, this hogging, here it is negative moment, hogging, here anti-clockwise is the hogging moment. That is why the left anti-clockwise is negative and the right clockwise will produce a negative moment at the section. So, here also it is right of the section, it is clockwise moment. W is acting downwards. So, clockwise moment, so right clockwise is negative. So, we get minus W into the perpendicular distance. Here perpendicular distance is CB. Okay. Now, what is CB? We will take this, okay, CB, we will take this triangle. So, take triangle OCB, you get sin theta is equal to CB by OB, right? So, OB is the radius, OA is the radius R, OB is the radius R, OX is also radius R. So, CB is equal to OB is of radius R, so R sin theta. So, from this we get M theta is equal to minus W into CB is R sin theta. Now, so that is all, okay? That's all the moment. Now, we have to find the distribution of moment. What is the moment at B? What is the moment at X? And what is the moment at A? So, this moment depends upon W. W is constant. It is concentrated load, not going to change. R, radius is constant, not going to change. So, only variable is theta. So, this moment, bending moment depends upon theta. So, as theta varies, your bending moment also varies. So, first of all, at B, your theta is equal to 0. So, from that, your M theta is equal to minus W or sin theta. Sin 0 is 0, right? So, your bending moment is 0. Now, we will come for section X. So, at X, theta is equal to theta. That means your M theta is equal to minus W or sin theta. Now, we take A. So, at A, theta is equal to 90 degree. perpendicular, right? 90 degree. So this is perpendicular, 90 degree. So m theta at A is sin 90 is equal to 1. So you get minus WR. Okay, so it is a 0 minus WR sin theta and minus WR. So we don't know the value of theta, it varies. So from B to A, depending on theta, it varies from 0 at B to minus WR at A. That is, the minimum value is 0 at B and the maximum value of bending moment is minus WR at A. Okay, so this at B you have the M minimum, bending moment minimum, and at A you have the bending moment, maximum bending moment. So 0 and at A it is minus WR. Okay, so again see your W is a concentrated value, this R is the radius, right? So from B to A it is curved, R radius means again it is curved. So how can we draw our bending moment diagram? So we will draw the bending moment diagram now. So first of all we will draw our beam. So this is our beam. This is A, B, and we will find the midpoint. So this is O. Now we will mark our bending moment. At B the bending moment is 0. At A the bending moment is minus WR. Okay, it is minus WR. So from A it is minus WR, it is curved, and at B it is 0. So it gets reduced and at B you will get 0. Okay, at B it is 0. So everywhere it is negative. The bending moment is negative everywhere. So this is your bending moment diagram for a curved beam, forming a cantilever curved beam forming a quarter of a circle. Now, for curved beam, in addition to bending moment, we have twisting moment also. So our step 3 is finding the twisting moment. So I will write here step 3. So step 3, the twisting moment. So what is twisting moment? See, bending moment is the summation of the load multiplied by the vertical distance CB. Perpendicular distance CB. Now twisting moment is this load multiplied by the distance CX. Okay, CX, this distance is responsible for twisting moment and CB is responsible for bending moment. So for twisting moment it is W into CX. So as we did the bending moment, again the moment is negative. So here m theta is equal to minus W into CB. Here it is minus W into CX. So we will take twisting moment. So twisting moment at X. We will take it as t theta, because at x it is forming an angle of theta, is equal to minus w into cx. Now we will find what is cx. So cx is equal to this r minus OC. R minus OC. That is equal to r minus, what is OC? You take triangle OCB. OC is equal to r cos theta minus r cos theta. So we get Cx is equal to r into 1 minus cos theta. So our twisting moment at x, t theta. So at x, t theta is equal to minus WR into 1 minus cos theta. Now we will find that what is the twisting moment at B and what is the twisting moment at A. At B, theta is equal to 0. At A, theta is equal to 90 degree. So at B, theta is equal to 0. So our twisting moment at B will be equal to. So twisting moment at B will be equal to minus WR into 1 minus cos 0. So cos 0 is equal to 1. So you get 1 minus 1, 0. So 0 multiplied by minus WR, it is 0. So you get 0. Now at A, theta is equal to 90 degree. So you get a twisting moment at A is equal to minus WR into 1 minus cos 90. You know cos 90 is equal to 0. So this value is 1 minus 0, 1. So we get minus WR, minus WR. So similar to that of bending moment. So for this case, this particular case, twisting moment and bending moment is similar. So now we can draw the twisting moment diagram. So twisting moment diagram is also same as that of bending moment diagram. Anyway, we will draw that. Okay. So this is A, this is B. So if we can take this point as O. So twisting moment at A is minus WR. Minus WR. Twisting moment at B is 0. So okay, so this is minus. This is twisting moment or torsional moment diagram. Now our last step is determination of deflection. So you have already studied in your structural analysis 1 the method of strain energy, how to determine the deflection using the method of strain energy, etc. Right? So I hope you remember the formula. So I will write it here. So step 4. Step 4 is deflection at free end B. Deflection at free end B. We are going to find the deflection at free end B. So we know by using the method of strain energy, the formula for deflection, that is strain energy formula is, we know strain energy equal to, strain energy will be represented by U. So we know the strain energy formula. Strain energy is represented by U. So strain energy U equal to integration of m square ds by 2ei. m square by 2EI into ds. So here m is m theta. This formula is familiar for you. You have studied it in your structural analysis 1 in strain energy method. Now, for this particular case, since this is a curved beam, in addition to the bending moment, you will have torsional moment also. So, it is plus integration of t theta square by 2gj into ds. Why it is gs is g? Here bending moment is m, twisting moment is t, 2 is the same, E is modulus of elasticity, G is modulus of rigidity, I is the moment of inertia, J is the polar moment of inertia. So now we know what is m theta and t theta at section x. So now we know the beam is varying from theta varies from 0 to 90 degree. So integration is taken from 0 to 90 degree. 0 to pi by 2. 0 to pi by 2. We know the value for what is m theta and t theta. Now, our aim is to find ds. So, what is ds? So, for ds, you consider a small stripe in the beam AB. Okay. So, that smaller stripe you can write like this. Consider a small stripe. So, this smaller stripe is ds. And this ds, this portion, it makes an angle of, this ds makes an angle of d theta with O. Now, this ds will be equal to r into d theta. If you consider theta is small, d theta is small. So, ds is equal to r d theta. Okay, so ds is r into d theta. R is the radius. R into d theta. Okay, now we will substitute. We know m theta is minus wr sin theta and t theta is minus wr into 1 minus cos theta. So now just substitute these values. So what we get is u is equal to u is equal to integrate one, you can take 1 by 2 EI outside. So 1 by 2 EI into integration of 0 to pi by 2 multiplied by m theta square, that is minus wr sin theta the whole square into ds is r d theta plus 1 by 2 gj into integration of 0 to pi by 2 t theta is minus wr into 1 minus cos theta the whole square into ds is r d theta. So we get 1 by 2 EI into, you can take this minus square, it is plus, w square out, you can take w square r cube, r square r cube into integration of 0 to pi by 2 sin square theta into d theta plus 1 by 2 gj into, so minus square, so w square again r cube, this r square and this r, so r cube into integration of 0 to pi by 2 into 1 minus cos theta the whole square into d theta. Now this will be equal to 1 by, okay, you can write it as w, you can write it as So this will be equal to 1 by 2 EI. Okay, you can write it as W square R cube by 2 EI into integration of 0 to pi by 2. Sin square theta can be written as 1 minus cos 2 theta by 2. Sin square theta, differentiation of sin square theta is written as 1 minus cos 2 theta by 2 into d theta plus W square R cube by 2gj into integration of 0 to pi by 2. It is 1 minus cos theta the whole square, right? 1 minus cos theta the whole square. This is written as this is in the form of a minus b the whole square. So you can write a square minus 2ab plus b square. So plus cos square theta into d theta. So you can take this 2 outside, So you get W square R cube by 4 EI into 1 into d theta. Differentiation of d theta, that is theta, minus cos 2 theta. Differentiation of cos 2 theta is sin 2 theta by 2, 0 to pi by 2 plus W square R cube by 2gj into integration of 0 to pi by 2 into 1 minus 2 cos theta plus cos square theta. Cos square theta can be replaced by 1 plus cos 2 theta by 2. So 1 plus cos 2 theta by 2 into d theta. So you get W square R cube by 4 EI into when theta is equal to pi by 2, it is pi by 2 minus 1 by 2 into sin 2 into pi by 2. Then minus theta is 0, sin 0 is 0 plus W square R cube by 2gj into integration of 0 to pi by 2. You can take 2 as the LCM. So you get 2 minus 4 cos theta plus 1 plus cos 2 theta divided by 2 into d theta. So here you get W square R cube by 4 EI into, this is sin 2 and 2 get cancelled. So here you get pi by 2, sin 2, this 2 and this 2 get cancelled. So sin 190 is 0. So we get W square R cube by 4 EI into pi by 2 plus W square R cube by, you can take this 2 outside, so you get 4gj into differentiation of 2 into d theta, this is 2 theta, I will take it together, see 2 plus 1, so 3, so differentiation of 3 into d theta, we get 3 theta. Now minus 4 cos theta, minus 4 into differentiation of cos theta is sin theta plus differentiation of cos 2 theta sin 2 theta by 2, 0 to pi by 2. So we get W square R cube by 4 EI into pi by 2 plus W square R cube by 4gj into 3 into pi by 2. So 3 pi by 2 minus 4 into sine pi by 2 plus sine 2 into pi by 2 by 2. When you substitute 0, everywhere it is 0. Sine 0 is 0. Sine 180 is 0. So you will have only this terms, right? So here you get sine 180, this term becomes 0. So sine 90 is 1. So what we get is, you can take W square R cube by 4 outside. So you get pi by 2 EI plus 1 by Gj into 3 pi by 2 minus 4. So we get which is equal to W square R cube by 4 into pi by 2 EI plus, you can take LCM of this, we get 3 pi by 2 Gj minus 8 by Gj. So now we know the Castigliano's theorem. Deflection is equal to dou U by dou W. So delta at B, delta is equal to, see the Castigliano's theorem is delta is equal to dou U by dou W. So dou B is equal to dou by dou W of U. So here U is W square R cube by 4 into pi by 2 EI plus 3 pi by 2 Gj minus 8 by Gj. So delta B is equal to, we can take this as constant, right? So we get pi by 2 EI plus 3 pi by 2 Gj minus 8 by Gj into R cube by 4 is also constant. So remaining thing is 2W. So we get 2W R cube by 4 into pi by 2 EI plus 2W R cube by 4 into 3 pi by 2 Gj minus 2W R cube by 4 into 8 by Gj. So we get 2 gets cancelled. So pi W R cube by 4 EI plus, we will take W R cube by 4 Gj out. So we get 3 pi minus 8. Here 2 gets cancelled. We are taking 4 W R cube by 4 Gj out. So we get 3 pi. Here W R cube by 4 Gj out. Okay, here, okay. It is 2W by 2. Sorry. So some mistake somewhere. Eight by two GJ. Here it is two GJ. So 8 by 2 GJ, 8 by 2 GJ, 8 by 2 GJ. So you can cancel 2, 2. Now it is correct. So this is your answer. This is your deflection. So deflection, your answer is deflection delta B is equal to pi W R cube by 4 EI plus W R cube by 4 GJ into 3 pi minus 8. So now we have analyzed our curved beam, a quadrant of a circle, the shape of the quadrant of a circle for shear force, bending moment, twisting moment and deflection. So that's all. First example is over, and for your exam point of view, you may be asked instead of W, sometimes you may get some value. W in terms at W you will get some value. So you can derive it and you can substitute the value in the place of W. So if you remember what is the formula for shear force, bending moment, deflection and torsional moment, you will be easily able to solve the problem and analyze the problem and for drawing the diagram. So thank you.